Okay, so let's draw methanol using the um, what I'm using, which is I believe Spartan 18 um, version of the program. The Carabine Lab has Spartan Student, which isn't that much different than the full-blown version that I have now. So there is a tutorial on how to use this in the folder. I just put it in there. When we get back on campus, if you ever wanted to use this program, you could go in the Carabine Lab in the chemistry department, and the software is there for you to be able to use. So let's first of all draw the structure of methanol. So drawing the structure of methanol, I click on this button called New Build, and let me just double check here that we are actually capturing the full screen, which I hope we are. So in terms of this build, let me just kind of walk you through and see all the different things that I can build with this builder tool. First of all, I have an organic modeling kit, which means I can have an sp3 hybridized carbon, an sp2 hybridized carbon, an sp hybridized carbon. I can have a carbon like what would be in a benzene ring, where it's partially where it's partial double bonds. I have the standard elements like nitrogen, oxygen, sulfur, silicon, hydrogen, fluorine, chlorine, bromine, iodine. So I can draw anything if I want rings. I have a ton of rings that I can just plop into my building area, which is in green. I have groups that I can choose from. So in terms of my groups, I can choose all of these different types of groups. So I don't have to draw them. I can just kind of plop them in, and then we can do calculations on them. Now let's say, okay, great. If I go into the inorganic mode, I can do a lot of things. And I can, if, we keep telling you, don't draw carbon with 5 bonds or you'll lose points. In this program, I want a carbon with 5 bonds. I can go to the inorganic mode, which basically means I can select carbon. I can come down here and say, you know what? I want a carbon with 5 bonds. Now the computer calculation may blow up because we're not allowed to have 5 bonds to a carbon, but it doesn't mean I can't draw it. Then the calculation will say, yeah, we're stopping here because you've done something illegal. But I can draw any element in any geometry that I want because I have a periodic table. And if I want to know what is available through all these different programs like AM1 or PM3, if I click on it, only the elements in green I can do calculations with. If I want to go to something which we will later, or we won't today, but I do routinely, if we want to go to a Hartree-Fock ab initio calculation with a 321G, it's not 321G star, 321G. If I click on that, I have a lot more elements to choose from. So these are purely Schrodinger equations, whereas PM3 has my friend lithium here, but it also, see, it doesn't have sodium and potassium. I had to buy a completely different program in order to do those alkali metals. So we have a lot more flexibility in the inorganic mode. We also have some biochemistry mode, molecular biology building modes. So for instance, if you want to draw a peptide, you have your amino acids, and you can basically choose the sequence that you want. So you could say, well, I want a glycine, threonine, leucine, that's that, proline, histidine. I can generate that sequence, and then actually if I come over here and click, double click, it puts that sequence into the drawing space. So I can do that. I can also choose, do I want this in an alpha helix? Do I want it in a beta sheet? I can change angles. I can say, well, do I want strand A or strand B? So a lot of power here in terms of drawing biomolecules. And we can, I'm going to get rid of this. I'm going to go back into my build mode. We have a nucleotide mode, so ACGT. I can build a sequence from that. I can say, okay, I want a GACTGTC, and then I can click over here, and that will come in. And if you notice, the molecule came in with its corresponding other strand. So in other words, you have whatever this group is, and then you have the corresponding strand that, or the other corresponding group that hydrogen bonds to it. Or I think it's A and T and G and C. So it'll actually build the both of the helix. I think if you go A, I'm not quite sure what that does, but we could go with a single strand. If I wanted to build it, I built it, unfortunately, with a double-stranded DNA. So if we wanted to, we could build a single strand. So we have the ability to really put in a lot of biomolecules, and I'll show you that with the now infamous coronavirus. So let's go ahead and close this out. And no, I didn't want to save that. Let's go ahead and close it out, and now let's talk about methanol. So we went from these really complicated structures to methanol. I want methanol. I want an sp3 hybridized carbon. You can see that I can rotate around. Yellow bonds are where I can add things. So let me go ahead and add an oxygen to that. And then there is my methanol. I'm not quite sure what that is. If I hit the looking glass, there is my methanol molecule. I can slide it across the screen. I can make it bigger. And so I can make my methanol molecule. And I can visualize this a number of different ways. This is the equivalent of the molecular models that you guys have, that you use for class. But I have a lot of other choices. I could make this a tube, which I like to do a lot because it makes things easier to see. I could make this a space filling model, where now I can see the actual van der Waals radius of the atom. So I get more of an idea about shape. How big is a methyl group compared to an OH group? And then there's some other things that I have the ability to do, which I'll show you. We can do ribbons. So you see those in your biochemistry, biology, genetics books. I'll show you an example of that with the coronavirus in a moment. But we can basically flip back and forth between all of these different visualizations, which makes it really helpful if I'm trying to look at the structure. All right, so this is just the visualization part. We can rotate, we can size, we can see different types of the structure. Now let's talk about calculations. So let's set this up and let's do a calculation. So let's come up here to my setup and let's set up a calculation. And when I set up a calculation, it asks me, well, what do you want to do? Do you want the equilibrium geometry? And everything is pretty much in the gas phase. And what I mean by that is the molecules are isolated. It's a single molecule in space. If you want molecules to start interacting with each other, you could do, in these calculations, you could do a nonpolar or a polar solvent or water, but those are going to increase your computational time, and you really got to know what you're doing. I don't think I've ever done a calculation so far in anything but the gas phase. And there are limitations because these molecules are not just totally on their own. There are interactions, intermolecular interactions. Now I get to choose what method I want. So DF is density functional theory. If you want to learn about that, you can hover over it and it'll tell you how to do that. I like something fairly straightforward, which is going to be semi-empirical, and I like PM3 because I'm familiar with what it does with lithium. So we're going to do an equilibrium geometry. That means it's going to try and find the most stable conformation of the methanol molecule. So all I do is say submit. It knows it's methanol, which is built into this program, and then I go ahead and say save. And so it just started my calculation, and now it just ended my calculation. I mean, that could have been an hour process when I was back in graduate school. Doesn't look like much changed because, to be honest with you, there wasn't many atoms to move, any bonds to really change. But now what I can do is now I can begin to look at this molecule, and let's look at a couple of things. So now what I have the ability to do is I have the ability to look at surfaces. Well, what kind of surface? Well, let's see. What can I add to this? I could do a HOMO-LUMO. For most people, that's not something we've really talked about. I could do a density plot, so I'll put that in. How about I do a electrostatic potential map? And usually those are my big two. If I want more surfaces, then I can do a density potential. I can mix these things in and out. And maybe I'll come back to that and do that. There's one I'm having a very difficult time doing. So I already did that one, so let's go ahead and delete that. So all I have to do now is just say, okay, I want to see what the density looks like. A density map just is a non-color coded space filling model. So here is where the electron density is in the molecule. Again, atoms aren't coded with colors in real life. So that's the size of the methanol molecule. If I look at my electrostatic potential map, these kinds of plots I love. Okay, so what does this mean? Well, the blue is areas of delta positive, the red is areas of delta negative. Now you might say, well, I'm having a hard time seeing my methanol molecule. Great, let's click on it. I'm going to come down here and I'm going to go, you know what? Let's do a transparent. So now what it does is now it superimposes that surface on the model, so I can say, oh, where's the delta minus charge? Right over the oxygen. Where's the delta positive charge? Right over the hydrogen, exactly where we would expect it to be. So I can do that. I can get some pretty cool looking. I can get the meshes. Sometimes the meshes are really cool. Some of our artwork in the chemistry department on the third floor, I created some of these, now in circa 2003, and we had the graphic artist kind of incorporate those in our chemistry art. You can also do dots, which aren't helpful. They're never helpful. And you can just do a solid, which is what we started with. So again, for methanol, not exciting, but for a bigger molecule, it might be. Let's see. I can also do, and let me just see if I can remember how to do this. I could do a potential, against my better judgment, I'm going to do a potential map. Yes. A potential map. What is that? That is the mushroom shape of the sp3 hybrid orbitals of oxygen that have the lone pairs in them. So now I can visualize where the lone pairs are in the molecule. And if you're saying, but wait, shouldn't it have like rabbit ears? Well, electrons can move. So those two normal sp3 orbitals with the lone pairs, they look like a mushroom. So we can actually visualize the pi bonds. We can visualize the lone pairs in the molecule. And that might be helpful in a molecule, because if I'm going to add acid to it, where's it going to go? To the lone pair. So maybe I can visualize that in my molecule. So a lot of power here simply by clicking, and it gives me a lot of different information that I can get. I can only get these surfaces, these plots, using at least semi-empirical methods. So that's pretty useful and kind of a demonstration of things you can do. So we can do surfaces. There are 3D glasses that go with this. They are not tremendously great. Most of them are cardboard, but they will give you kind of a general 3D image. The best thing to do is to couple this with virtual reality, and then you can really walk inside the molecule. But that's a case study for another time. Okay, case study number 2 here, besides methanol, is how about biomolecules? Well, you can look at DNA, you can look at RNA, you can look at other bioorganic molecules, enzymes. You can draw them from scratch using the builder, which I showed you, or you can get them from what's called the Protein Databank. Now, the Protein Databank is where you determine the structure of a molecule using X-ray crystallography. What seems like 3 years ago, when we first started spectroscopy in the lab, I talked about the idea that if you grew a perfect crystal of a molecule and you passed an X-ray beam through it, you would diffract the X-ray beam and be able to figure out the structure of the molecule. I did small molecule crystallography when I was a postdoc at Brown. I send my structures away now, but there are people who do bioorganic, biomolecular X-ray crystallography on things like proteins, and the example that I'm going to show you is the infamous coronavirus. Now, let me go to my coronavirus page right here. So, unbeknownst to me at the time, the molecule of the month on what is called the Protein Databank, which is run by the Royal Chemistry Society in Britain. Coronavirus was the molecule of the month in February of 2020. How ironic. And you can, I put the link in here, so if you're really interested in like coronavirus stuff, here is the coronavirus proteases, and it has a lot of information as of February about this. It has, for instance, it's SARS-CoV-2, which is the 2019 novel coronavirus that is commonplace. It's currently posing a danger in Wuhan. That was in February of 2020. Things have gotten much, much more serious since then. And it shows the protease with this blue thing, which I believe is an inhibitor molecule that they were looking at or tried to look at. What they had to do is they had to take this protease and get it into a single crystal in order to get these structures. These are really kind of artistic views, but there is, and I'll show you, there is actually carbons, hydrogens, oxygens, the whole 9 yards with this as a huge organic structure. Now, in the Protein Databank, everything is given like a 5-digit and number code, so that if I know that, I can click on it and download the file. Let's click on this one. So this is the main protease of the coronavirus that makes cuts. If I click on that, I'll go to that page. It will give me actually something that I can view on the web. It gives me a lot of, it was determined by X-ray crystallography. It gives me some variation type stuff, but I can actually download the file. I'll download the file again. I already downloaded it. PDB stands for Protein Databank. So if I download the Protein Databank, it's going to go into my downloads, and now I can actually go back to this Spartan program. I can close out my methanol. I won't save any changes to it. Now I can say, you know what? I'm going to open up in my downloads here. I'm going to open up I'm going to open up that protein databank file. So I click on it, and there it is. There is the coronavirus protease. Now, for those of you who have taken genetics or know a little bit about biochemistry or even in biology, these are the cartoons, right? These are showing the helical structure in red, whatever these, I guess there's beta sheet in blue with the arrows. There's more helical structures in red, and then this pipe cleaner like green thing is just kind of traces the backbone. You might say, oh, well, there's a molecule that looks like an organic molecule. That's the inhibitor that they actually, what they're calling an inhibitor that they grew the crystal with. This is where I can go to my model and I can say, you know what, fill this in. So let's fill it in with ball and spokes. So there is the actual organic molecule. If I want, I could look at it with the tubes, which I kind of like. I can get rid of the cartoon if I don't like that. I can get rid of the ribbons. So now I've got the protease here in its true organic glory. I can zoom in on it. Let me try and zoom in on it. There. I can start zooming in on it. For those of you who are saying, like, what are those yellow? What are those bright yellow atoms? Those are SH. Those are thiols. So, for instance, for those of you who've talked about protein structure in your general biology class, let me orient it and let me kind of let me shift it over the center of the screen. This SH right here and this SH, so that would be an example of two SHs that are close together, that if you've ever heard of a disulfide linkage, that's where a disulfide linkage could occur. In this structure, there's no disulfide linkage because otherwise you would have the two yellow atoms actually attached to each other. These little kind of balls are water because this was crystallized from water. We have things in here like benzene rings. Blue is nitrogen. So if I want to, I can really take a look at, blow up the molecule and begin to take a look at it. And I haven't gotten a chance to look at, but I know that there's a virtual reality component that you can do with this. We do have virtual reality systems in the chemistry and in the math computer science department, and so I could actually upload this and I could go into it in the virtual reality world. And if you're like super interested in that, there's a company called Nanome, Nanome, and they had a town hall where the scientists were in the virtual world as little blue guys, and they were looking at the protease, trying to talk about what kinds of drugs would potentially fit into active sites to try and see, okay, now what kinds of therapeutics might we begin to design based on the structure of this COVID-19 protease. And of course, that doesn't take into account any mutations and all of the other complications, but there were people who were using virtual reality, just like we actually have at John Carroll, going through, and like I said, I haven't gotten a chance to take a look at that, but I will at some point, because it's a perfect application. But this is what we could do. So here, this is one of the COVID proteases, which is why we're watching this and not participating in it. So you can do any of the biomolecules, and you can begin to do this. You could begin to do some calculations on this if you wanted to. If you know what you're doing, you could take some small molecule that might be a therapeutic and calculate where it might stick in this molecule or how good it would fit into some sort of active site if that's what you were targeting in your drug design. And the beauty of this is we can do a lot of this work on the computer without having to go to the lab and synthesize every single molecule. We might have some targets that we can then go to the lab and synthesize. So molecular biology is not my particular area or strength of area, but I know how one would use these types of pictures. So we can do biomolecules as easily as we can do organic molecules. All right, so that's an example of drawing DNA or RNA using something that is ripped from the headlines of today. Now, let's take a trip back to boring first semester organic chemistry. Case study number 3 that we'll do. There's 3 case studies that we're gonna do, but then I'm gonna leave you to interpret the results as part of your online lab report. So let's go back to when you first started talking about Newman projections last semester. We have a gauche conformation of butane, and we have an anti-conformation of butane. And the question is, which one of those is more stable? Why? But what I want to answer actually in this, using the computational aspect of this, is by how much? Right? If I said, which one of these is more stable? Hopefully, if you've made it this far, you would say, oh, well, the anti, of course. And you'd be correct. But then if I said, how much? By how much? Better yet, if I have 100 molecules in the Gaussian, or 100 molecules of butane, how many of them are going to be anti? How many of them are going to be gauche? Could you even make an estimate of that? So this will let us actually determine that using these computational calculations. So let's go back. Normally this is what you would do in the lab. Sorry, you can't do that. Trust me, I am very sorry that you can't do that. So let's go ahead and let's draw both of those conformations. I'm going to use some advanced methods that I can use with this. So let's go to build, and let's take our sp3 hybridized carbon, and let's go carbon, carbon. Okay, so there is my, let's call this the carbon-2, carbon-3 bond. So looking down the carbon-2, carbon-3 bond, where do I want to put the methyl groups to make this anti? There and there. And now if I hit the sunglasses, here is my anti conformation of butane. Now, if I know what I'm doing here, I can say, you know what, give me a new molecule, build a new molecule, and don't worry, the other one doesn't disappear. Let's draw the gauche. So now let me draw my carbon-2, carbon-3 bond again, only in this case I'm going to draw the gauche conformation, which means I'm going to go here, and I'm going to go here. And so now I have my gauche conformation. Okay. And where did my anti go? Actually, I can go back here. There's my anti, there's my gauche. Okay. Now, let's do a calculation and figure out what the energies of those two molecules are. So I'm going to go to set up a calculation. I'm going to say let's do an equilibrium geometry in the ground state. So find the equilibrium geometry for anti, find it for eclipsed, or sorry, gauche. They're both staggered, not eclipsed. And let's go ahead and just use semi-empirical calculations. All right, so if I do that and I say submit, it knows the name of one of them but not both. So I'm going to go ahead and say let's use butane, anti, and gauche. We'll call it that. And so now it's going to do one calculation and then it's going to do the other on top of it. and it's done with both calculations. All right, now I changed the molecule back and forth down here. So here is my anti-conformation, and here is my gauche conformation. Great, didn't really change that much, but now let's talk about the energies of these. So what I like to do is the following. I like to create a spreadsheet, and again, I can do this with the full-blown $1,600 version of this software. I can go ahead and say, here's molecule 1, anti, here's gauche, and I can come over here and say, you know what, I would like to look at the relative energy of those two molecules. And so I click on it, and now let's take a look at these two energies. Okay, so first of all, molecule 1, the anti, has a relative energy of minus 2 kilojoules per mole. The gauche conformation is 0. Now let's take a little quick back look, a look back here, and let me go ahead and create a slideshow so I can go ahead and draw something out here on the screen. Let's see. Let's put our energies in here. So putting our energies in here, the anti-conformation we said was minus 2.13 kilojoules per mole. And the gauche conformation was 0 kilojoules per mole. Well, something has to be 0 because I asked for the relative energy. Now, in your energy coordinate diagram, the larger the energy, the less stable the conformation. The lower the energy, the more stable. So in this case, minus 2 is smaller than 0, and so the anti-conformation is indeed the more stable conformation in this equilibrium, and the larger number, which in this case is 0, is the less stable conformation. So I have my less stable conformation and my more stable conformation. So just like you learned in lecture, we haven't destroyed anything you've learned in lecture, the anti is more stable than the gauche. But now I can say by 2.13 kilojoules per mole. And then your next question is, I can't relate to 2.13 kilojoules per mole. And I agree. When you first start thinking about thermodynamics, is 2 kilojoules per mole, if a reaction gave off 2 kilojoules per mole, is that going to warm my hand? Is that going to explode? How much is 2 kilojoules per mole? So fortunately, we can calculate this equilibrium constant based on that difference in energy. So if we look at this, if we look at that, the calculation, I'm pretty close. I've done this calculation before, so what I have is I have the energy of anti minus the energy of gauche. I asked for the relative energy, so I went right there. And we got minus 2.13. I think the last time I did this calculation, I got minus 2.17. Close enough. Now, my equilibrium is gauche in equilibrium with anti. So that means the KEQ is the KEQ is going to be the concentration of anti, or the amount of anti over the amount of gauche, right? Products over reactants. Now, the difference in energy here, I'm going to approximate as a free energy delta G difference. Is it truly that? No. But for our purposes, it's fine. Now we know from general chemistry that delta G equals minus RT ln K. So in theory, I can calculate K by rearranging the equation. So the final equation going through all of this would be that the equilibrium constant, if I know that delta G difference using the gas constant in its energy format of 8.314 joules per mole per Kelvin. If I say I did this at 25 degrees, which are the way calculations work, then I could plug in R at 298 for 25 degrees Celsius, do that calculation, and I can get this equilibrium constant for that calculation. And once I have that what I have the KEQ calculated, again, that would be the concentration of the anti over the concentration of the gauche, concentration of products over the concentration of reactants, right? That's our equilibrium constant. So basically, once I know what that KEQ value is, I can do some more mathematics, which maybe I do on the next slide. Nope, I don't. I'm going to cut right to the chase. Once you figure this out, once you figure out the delta G and what KEQ it gives you, and then from the KEQ, you would have, you could say that, you can calculate the percentage. I'm not going to go through the math on that. You create a chart, which is what I create. And I create a chart where, it's kind of hard to see this, but it is in the handout, where I can plot the delta G difference versus KEQ, the KEQ that's corresponding to that delta G difference, and then it'll tell me the percent products and the percent reactants. The percent products in this case is the percent anti, the percent reactants is gauche. So I got, for a delta G difference, minus 2.13. I go through my table, and minus 2.13 is like right here. That means the equilibrium constant was between 2.2 and 2.4. So the KEQ here was between 2.2 and 2.4. That's the concentration again of anti to gauche. Basically what that means is, that means it was 2.2 over 1. So then I could calculate the percent of anti and the percent of gauche, and sure enough, I just do that in a spreadsheet, and it tells me that for this molecule, it's, let's take an average, about 70% anti and about 30% then gauche. So if I had a collection of butane molecules, 100 of them, and I stopped them and counted up how many were anti and how many were gauche, I would end up with 70 antis and 30 gauche. So 70% of butane molecules are in the anti conformation, and 30% would be in gauche. Now, I'm going to do another calculation, but we're not going to work through it. You're going to work through it. And one of the questions that I'm going to ask in the online lab report is just a real quick, is 70-30 in this case? Is that something you would have predicted? Does that seem high? Does that seem low? You probably haven't even thought about that. But if I would have said, hey, estimate the number gauche, estimate the number anti, whatever number you would have chosen, would it be 70-30? So that's what that difference is that we talk about in lecture when we say this one's more stable. What we mean is 70% of those molecules are in that conformation and 30% are in the other conformation. So we can get this information about these different conformations, and if you go back and remember all of the Newman projections you wrote, we could actually do that for all of those different conformations and lay out what percentages of the molecules were actually in each one of those conformations. You might say, well, that's a great exercise, but what's the reality of that? Reality of that is if I'm trying to find a molecule that's going to fit into some sort of coronavirus protease and stop it from doing whatever it is that it's doing, and it has some different conformations, I can't really generate the shape of the molecule unless I know what the major conformation is. So in drug design, this is a very important issue. And I just did this in 10 seconds. So that is, in my perspective, that's pretty amazing. Okay, so that's how we go through that whole process. So now let's go to